Describing the voltage gated sodium channel. And specifically as it pertains to the action potential. Okay. Let's describe the conditions and the mechanism here again. So our channel is essentially voltage sensitive. Okay. In that, it's going to open at negative 55 millivolts and then close at positive 30 millivolts. The other thing we want to say here is that there are two gates on this channel. So two gates, and I'm going to kind of color coordinate them here so we can keep track. First is our activation gate. Okay. And this is only voltage dependent. Okay. Then we have our inactivation gate. And we said that this is both voltage and time dependent. So voltage and time dependent. Okay. So having said that, let's go ahead and look at the three states of this channel. Let's look at three scenarios here. First off, our channel is at rest. So this is the resting state. This is when the membrane potential is negative 70. And if you look at the channels, let's draw a little channel here. This little passageway, and we're going to draw in our two gates. Our activation gate in this state is closed. So we're going to draw these two closed shut, right? Our inactivation gate in this instance is open. So we're going to draw our inactivation gate here as being open. So let's describe the state of the channel at rest here. So our channel is closed. But it is incapable. Even if we did have a membrane potential change, or excuse me, it is capable. I'm sorry. Let's do this again. Oops. There we go. So the channel is closed, but capable of opening. All right. And what this means is that our activation gate is closed. Our inactivation gate open. All right. So if we did receive a negative 55 membrane potential change, the channel is capable of being opened because the inactivation gate is open. Let's shift and look at the second state of our channel. So if we did get that strong enough change, now we're looking at the depolarizing state of the channel. So this is when the channel is now open and we have depolarization happening. And the membrane potential here is going to be negative 55 millivolts all the way to positive 30, let's put this in arrow, positive 30 millivolts. Okay. And again, let's draw our little channel. Oops. It's a weird looking channel. Okay. Okay. And now in this instance, both gates are open. So let's draw both gates open. Activation gate as well as the inactivation. Okay. And then just to describe this, we now have a state where the channel is open. And that is because activation gate is open. And activation gate is also open. All right. However, want to add the small little additional detail here is that 1 millisecond. So 1 millisecond after our negative 55, right? We're going to add the time delay here. Now we're going to have the inactivation gate close. So there's a 1 millisecond delay where the inactivation gate will close after 1 millisecond of the depolarization. So that is going to be synchronized with the final state of the channel. So when the cell is repolarizing, let's look at the third state of our channel. This is the repolarization phase. And this is going to begin at positive 30 millivolts. This is the time condition or the voltage condition for the activation gate. Remember, they're going to open at negative 55, but then they're going to close at positive 30. So there are two conditions here that are resulting in the closure of both our channels here. So essentially the inactivation gate is going to close and that's going to deactivate our channel temporarily. So in this repolarization state, we begin with our activation gate still open because this is going to be our refractory period. We'll talk about this later on, but this is going to still be open here. However, our inactivation gate is now closed. So even if we had a strong enough membrane potential, which is negative 55, the channel here is incapable of being open simply because the inactivation gate is closed. So in this third state, the channel is closed and incapable opening. So our activation gate is open. while the inactivation gate is now closed. Okay. And I just want to mention here, this is going to correspond with what we call the absolute refractory period. So the absolute refractory period. And this is a short period of time where the channel is inactivated so that we don't have another action potential coming along too soon before we can get back to rest. This is the idea behind the absolute refractory period. So the channel is incapable of opening. Now, when we get back to rest, we're going to alternate the condition of these two gates. We're going to close the activation gate and then open up the inactivation gate, and we're going to return the channel to this initial state. Okay. But we're going to come back to this term and describe a little bit more exactly the conditions that are required for the absolute refractory period. We're also going to compare this to the relative refractory period. So there are actually two refractory periods at the end of the action potential. And when we kind of get to that, we'll be able to compare and differentiate them, and this will make a little bit more sense. Okay, but for now, we want to really focus on the state of our channel and the gating mechanisms of both of the gates. Okay, I'm going to pause here for any questions. Okay, so let's keep going. I don't know why my and someone give me a thumbs up if you can still see the slides. For some reason, my camera view disappeared. Okay, awesome. Thank you so much. Okay, so let's move on and look at potassium's voltage-gated mechanisms. And potassium, we said, is a lot more simple. It is going to be activated at positive 30, and it is voltage and time dependent as well. So essentially, when we get to that positive 30 millivolts, potassium channels open up. There's only one gate on potassium channels, so it opens up right away. Potassium is going to rush out of the cell, all right? And then that is going to help bring the membrane potential back down to rest. So potassium's movement is more important for repolarization than even sodium, right? Remember, sodium channels are completely inactivated by the time we get to repolarization. So what is helping to correct or return or reverse that membrane potential is really the outward flow of potassium. So this helps to bring the membrane potential back down to being more negative. And this is an attempt of potassium to reach its equilibrium potential, which is below the resting membrane potential at negative 94. So when the cell is at rest, potassium channels are closed. As soon as the cell depolarizes, there's a timed component here. So that 1 millisecond of the inactivation gates closing is exactly synchronized with the 1 millisecond with which potassium channels will open up. So 1 millisecond after depolarization, is when potassium channels will open, and then potassium can move in the opposite direction and correct the membrane potential. Now, the channel is going to be inactivated during the refractory period. So as soon as we get back down to rest, it's going to go a little bit below that resting membrane potential, and then the channels will be inactivated. This is going to correspond with that refractory period in terms of sodium's movement. So right after we inactivate the inactivation gates on sodium channels, that is corresponding with the refractory period where the potassium channels are now going to be inactivated. So this is all really synchronized. This is what prevents the action potential from being different. The action potential is always the exact same change, right? It's going to be the same amplitude. It's going to be the exact same duration. It's going to last for the same amount of time. It's going to travel the same distance. So the synchronization of the gating mechanisms and the time component on both channels is what ensures that this is such a heavily regulated event, especially as it pertains to time. So there's one gate. It depends on voltage and time. And this is an example of negative feedback because we're now correcting that initial depolarization. We are moving the membrane potential back closer to set point, which is closer to -70, which is the state of the neuron at rest. Okay. So let's think about, again, just reiterating this concept. We're going to do that in several different ways throughout the rest of this packet. And now we're going to think about the action potential in terms of the direction and the size of memory potential change. So when we have the excitable membranes, so this is going to be our neurons, this is going to be our muscle cells. These are the types of cells that we're thinking about that have the ability to generate action potentials. Okay. Now, this is going to be a rapid depolarization, and it's going to be used for communication. So as we've been describing, this is how neurons send signals. So all of that, all of the components of essentially who you are, not just your physical movement, but your memories, your thoughts. This is all because of synaptic communication between neurons. This is what is allowing you to perceive from the world around you. So your visual perception, your auditory perception, your olfactory perception, your speech, all of these various components of your personality and your behaviors are really essentially neurons communicating, which is really fascinating, right? So large depolarizations is what is used to communicate from one neuron to the other. And this is essentially the instruction for much of our behaviors and so forth. So in neurons, the action potential is going to start at the axon hillock, travel down the axon length, so from the soma down to the terminal, and then from there, we're going to look at the neurotransmitter being released, which is how we transmit that energy from one neuron to the other. We release a chemical, and that chemical energy is converted to electrical energy when the neurotransmitter binds to that ligand-gated channel. Okay, so if we think about the positive feedback change, this is the initial change of the membrane potential. So just to reiterate this in a different way, so here's our resting membrane potential. Here is our upstroke or depolarization of the action potential. This is caused by the movement of sodium into the axon. And then because of the gating mechanisms we described, at +30, we're going to have movement of the membrane potential in the opposite direction. So now we go from +30 down below rest. So again, if we recall the reason that the membrane potential becomes negative, this is because potassium is leaving the cell. So because it's trying to get to its equilibrium potential, it's actually going to overshoot the resting membrane potential, and we refer to this type of change as a hyperpolarization. And then eventually it's going to self-correct and get us back to rest. Now, the self-correction here is really owed to the sodium-potassium pumps. So the sodium-potassium pumps are what sort of reestablish the resting membrane potential after the potassium channels cause the membrane potential to overshoot below -70. So this is why this takes a bit of time to get us back up to rest, right, or -70. And then we describe the initial change as positive feedback because we're going above, or we're moving away rather from set point until we reach +30. And then we can think of the opposite change as being a negative feedback loop. So from +30 down below the resting membrane potential, this would be an example of negative feedback. So this is yet another example of how positive feedback changes are short, temporary, and for a desired result. And then they ultimately feed back into a bigger negative feedback loop. Okay. And then just to kind of look at the second panel here and really look at the gating principles. So for the sodium channel, the gating activation gates on sodium channels are going to open when we get to -55. And then that timed millisecond condition is going to be triggered. And so after 1 millisecond, inactivation gates are going to close, which really corresponds with the membrane potential being way up here at +30. And at this time, now the channels are going to be inactivated. So the activation gates may still be open, but now the inactivation gates have closed because of that condition that we just described. And then we think about potassium's movement. So potassium channels are going to be activated at +30. So this is going to correspond with the inactivation gates on sodium closing when we get to +30. So now we're going to have our potassium channels open. Potassium can move out of the cell, and then the inactivation gate or the inactivation of that gate on potassium channels will result in the membrane potential going below. So it's going to move downward or become more negative. And then finally, we're going to have the sodium channels and potassium channels both being deactivated. And then the sodium potassium pump is what helps to correct the resting membrane potential.